Good afternoon, everyone. Thank you for being here. My name is Yuval. I'm Chief Commercial Officer of QuEra. We make neutral atom quantum computers. Just installing one at ICE these months. So very exciting times to be talking about HPC and quantum. And maybe we can go down the panel and quickly introduce everyone. So Sebastian, How about you go first?
Sebastian Hassinger, I'm with AWS. I'm a business development specialist in the field organization covering quantum technologies, which is primarily the Amazon Braket cloud service that provides access to QuEra devices, among other QPUs.
My name is Hanhee Paik. I'm a director of quantum algorithm centers and then Quantum-Centric Supercomputing partnerships. So I primarily accountable for all the partnerships in Japan and then Illinois. And in Japan, we have a largest quantum and HPC integration development and science research and development effort in Japan. And then I work with a lot of Japan team members to advance the quantum-centric supercomputing.
Hi, I'm Ikko Hamamura from NVIDIA. I'm leading quantum computing in Japan, and as Yuval said, in AIST, GCAD has ABCIQ supercomputer, and that supercomputer has GPU nodes. Our GPU more than 2,000 GPUs, and it will connected with QuEra's quantum computers. And I'm also collaborating with JHPC Quantum Project, especially University of Tokyo for HPC part. I'm very happy to talk here. Thank you.
And we're glad you're here. Sebastian, thank you so much for stepping in at the last moment.
We've done this before.
We've done this before, right. So when people think about HPC and quantum integration, do they really usually mean on-prem, Sebastian?
I mean, it's a combination, right? I think that the topic really got picked up in earnest by supercomputing centers, LRZ, Oak Ridge, and others around the world who were interested in QPUs as a new form of supercomputing resource in the future, and realizing that they would need to grapple with all the operational challenges of this completely exotic type of technology. But I mean, HPC means on-prem and cloud, so both of those modalities are being explored now.
So do you have an offering that you would consider quantum and integrated quantum and HPC?
Braket itself is integrated with the rest of the cloud portfolio, including parallel clusters, batch, and other HPC-related resources. And we just use them actually, great collaboration with NVIDIA. For AstraZeneca, we presented at GTC. It was a cluster of about 1,000 GPUs that we're doing pre-processing and post-processing with Braket, providing access to a QPU, for IonQ, for a quantum Monte Carlo process step in the end-to-end process. So we've done HPC and quantum in the cloud already, yeah.
And I might ask you at some point in the panel, why don't you have an on-premises solution? But hold that thought. So Hanhee, you guys, IBM, I think, have more on-premises quantum computers than maybe everyone combined. I don't know. Why is that the case?
Well, I mean, by the way, we are not only just doing on-prem systems to integrate with HPC, we also do through the cloud access. Actually, I was just at the University of Tokyo. We announced the new news, which is we are connecting actually Kawasaki system is on-prem, that's right. But we can, but Kawasaki system also actually is also provided through the cloud access. And that through the cloud access, we are also connecting to the University of Tokyo and Tsukuba University's Miyabi HPC. So right now, IBM will run like two quantum and HPC systems through RIKEN and then University of Tokyo.
Right.
But again, as Sebastian just said, I think the connection can go through absolutely the cloud access. And then we actually had a demonstration last year that we showed, we demonstrated the sample-based diagonalization, which is the quantum and HPC algorithms, through our cloud from the New York data center, and then the machine at the RIKEN.
So from your perspective, the HPC part or the classical part and the quantum part don't have to be co-located, right? One could be on-prem, the other one could be on the cloud.
Actually, I feel, so I think I saw Ikko's answer a little bit, but then the co-scheduling, the scheduling the job and then and then coordinating it between quantum and HPC was a big challenge when we are actually demonstrating that the SQD algorithms. So co-location at least have that benefit, because it was really hard to arrange the job schedules for remote locations in New York and then also in Japan. But I think also our new system coming in June will have the InfiniBand connection between on-prem system and then the HPC. So we wanted to actually see the benefit of that too.
And Ikko, why do you think that, I'm guessing that you think that both classical and quantum systems need to be co-located.
Yeah.
Why is that the case?
Yeah, there are lots of use cases, but before answering the question, there are interesting things. So IBM's machine and Fugaku supercomputer is in same building, but AIST's aviation IQ supercomputer GPU nodes and QuEra's quantum computer are different buildings. So latency seems might be important, and it differentiates the use cases. And if latency is very, very small, you can use a supercomputer as, for example, decoder for quantum error correction. For quantum error correction, decoding time is very short, so low latency is requirements. And for another use case, so even if the latency is large, there are many use cases. As Sebastian said, so AI for quantum is very, very important. And Hanhee said, so HPC and quantum integration, that is subspace method is so HPC diagonalize very huge matrices. This is very good for HPC, but sampling from quantum state is very good for quantum computing. Yeah, this is a very interesting collaboration, I think.
Sebastian, before quantum arrived, you already had many different computers, CPUs, GPUs, and other things on the cloud. What can the quantum people learn from the experience of operating a hybrid environment, even if one part of the hybrid is not quantum?
Yeah. No, it's a really good question. As you said, I mean, we in EC2 and ECS, the other classical compute resources, there's Intel, ARM, Amazon, NVIDIA chips, and I think it's really, these are very complex solution patterns and architectures. So time spent on discovery and time spent on preparation is really important, because the actual run itself may take, I think the AstraZeneca run was a week long or something. So you want to make sure that you've got the right approach overall, and then the optimized sort of circuit or code for each of the steps for whatever the underlying technology you're running on. So preparation is really important, absolutely. And Hanhee said scheduling is a big part of that.
I was curious, why is scheduling so difficult in such an environment?
I think, first of all, people do not want to waste the HPC resources. Yeah. So HPC has to run all the time.
That's right.
Quantum as well.
Huh?
Quantum is also.
Yeah, that's true too. But HPC may be a little bit more expensive at this point. Maybe. So but then HPC is used a lot more the people than quantum. I mean, quantum has a lot more limited users than HPC, right? So we have to kind of see. I mean, again, blocking the schedule for HPC is almost impossible. So HPC will run whenever our job queue is starting, which we cannot really predict. And then we have to sync the quantum job there. And then from quantum end, I think we can do a lot of work because a quantum job may be waiting. And then we can remove the, because once it's waiting too long, then sometimes it cancels, because we also don't want to waste. But we can probably remove that part. But then also that costs, the implication on that is we are losing money because we are waiting for it, right? So I think in some little bit of the user and the service perspective, this coordination is actually difficult to be more efficient.
So if I understand correctly, it's not that scheduling is difficult, it's that optimal scheduling is difficult.
Yeah, that's right. Yeah, exactly. I mean, it's not a technological thing. Yeah, like we just wanted to use our computational resources more efficiently.
And I think to Ikko's point, I mean, I don't know what the prices are, but the GPU per hour is a few bucks, right? And the quantum computer per hour could be thousands of dollars. So
that's right.
Usually you'd probably have the GPU weight.
Well, except that there's as Hanhee was saying, there's so many more users for GPUs at this point. There's production workloads, right? So the demand on the supply of GPUs tends to be continuous and already highly optimized. So in part, the Bracket Direct feature is a way of scheduling a reservation time, and that window can be allocated for when you know you're going to have the GPU capacity reserved.
So Ikko, I wanted to ask you, since everyone wants to run LLMs on GPUs, in ICE, ABC IQ, is that also going to run LLMs, or is that specific to quantum jobs?
ABC IQ can use both. So of course, simulation of quantum circuits and large language model, generative AI is also preferable to run. Yeah.
And Hanhee, given IBM's decades of experience in mainframes, how does that translate into QPUs? Is there anything that you guys have learned from operating mainframes that translates to QPUs?
By the way, I'm also sitting with my old IBM colleagues, Sebastian and Ikko. Both
They're not
of
that
them.
old.
Really?
And then, yeah, I mean, we
of course, I
overlap a
know,
little bit.
but
Yes,
Sebastian's
but,
not-
yeah, I mean, like, Sebastian probably have a more experience in the running the mainframe
saying I'm
part.
old, huh?
No, it's not
The
true.
old IBM colleague.
But he has some more experience. But I think definitely again, if you want to chime in, you can chime in. But I think operating quantum computing probably is a little bit different. Like, definitely we have a noise issues, and then quantum errors are kind of new to the quantum computer. Doesn't exist in the classical part of it, right? So they're like a little bit different aspect of that. But you should.
Can I share co-scheduling problem? Co-scheduling. Co-scheduling is studied at University of Tokyo, Ken Nakajima groups, and so the main interesting difference is quantum state cannot be copied due to no cloning theorem, but classical HPC state can be copied. So HPC job can stop and save and restart. So this makes interesting co-scheduling.
Yeah, I mean, to the mainframe point, I mean, I think that IBM has enormous experience with operating those types of highly expensive and optimized infrastructures. But as you're saying, Ikko, that we kind of think of different categories of hybrid solutions. So there's the tightly coupled classical quantum, where it's a hybrid job, right? And you may be VQE or QAOA. There's a very tight coupled loop between the classical and the quantum. And then on the other end of the spectrum is something like what you're saying, Ikko, where it's more loosely coupled, it's more workflow orchestration, and there's the freedom to potentially batch or parallelize or otherwise optimize the overall workflow for what resources you're dealing with.
When we sell a quantum computer, we also provide the people to maintain it, to keep it running so that the customer doesn't have to worry about, in our case, replacing a laser if something happens or fine-tuning something. How does it work in IBM? Do you maintain your own computers, or do the customers want to just do it themselves?
I mean, definitely we have the team of like a technical support team that we have to maintain. I mean, certain system-related things have to be maintained by IBM, of course. But I think maybe the question earlier was whether HPC experts can also maintain quantum computer. I think it's definitely possible. Like our Japan team, Quantum Japan team here in IBM Quantum Japan team, they're actually becoming expert in both quantum and HPC, which is probably the new generations of the technical workforces. And then I'm sure they're going to grow more and more. I mean, same as you guys, right? Like
Yeah, and actually going back to the example of LRZ, they worked with the QPU vendors, IQM and AQT, on the sort of operational challenges, and out of that came the Quantum Device Management Interface, QDMI, which is a a standardization of the integration and management tasks for. So there's shared responsibility, as Hanhee was saying.
So I have a question for all of you, and maybe we go from Ikko and then towards me, towards the old IBM guy.
It's not that old.
And the question is, where are we today in this? Not, I mean, I know where we are geographically, but where are we today in the HPC quantum integration? Are all the problems solved? What is the next frontier in terms of issues that we have to address?
Yeah, there are lots of problems for quantum HPC integrations, and how to say workflow design. Yeah, and so development tools for HPC guys and quantum guys are different. So quantum guys like Python and Jupyter Notebook, but HPC guys like C++ and batch type job. So these different culture, we need to understand and find the best way to use quantum HPC supercomputers.
I mean, maybe adding to that. I mean, I know again, everyone knows the answer, but I'm just going to reiterate before you go to the. I mean, work source like the workflow management, because now users are experiencing multiple computational resources like HPC and QPU, and how you can orchestrate it like a certain level of the like a step of the computation you use quantum, and the other one is HPC, and then how you orchestrate it. That actually requires like a new software. There are a lot of open source workflow engines like Prefect or and things like that. So now people using this to really like make sure that you have a smooth workflows, and then whenever you change certain codes of certain part, still it maintains the workflow, right? And resource management was what we were just talking about, that we wanted to use our computation resources more efficiently. And then it was an excellent point about the C++. So IBM has a Qiskit now, and Qiskit will be updated with a C++ integration such that it'll run the quantum-centric supercomputing, quantum plus HPC, the most efficiently. Yep.
Interesting. That's cool. Yeah, I mean, I think that on-prem supercomputing and HPC has a long history of homegrown tools, and I think that the pressure that we're putting that tooling under by combining not just classical and quantum, but on-prem and cloud, means that there needs to be more standardization and more productization of those frameworks, because I love open source software, but it does tend to, it can get fragmented, and that can add a lot to the challenges of workflow management and scheduling and all the rest of the things we're talking about. So I think that the community starting to look at these types of prototypes, demos of these end-to-end solutions is going to expose a lot of those challenges, and I hope that we can sort of work together on standardization of those tools.
If I may answer my own question.
Yes, please.
One of the things that we see is that there's a debate on when does quantum stop and where does the HPC start, in terms of when you, okay, I have a problem to solve. I don't care if it's 1% quantum or 99% quantum. How do I design an algorithm, or how do I co-design an algorithm that can, and as you mentioned, the programming environment is often different. That's before you get into CUDA and others. So I think that's one of the challenges. Now, Sebastian, you're running on your cloud multiple types of quantum computers. I think you should be running just one, but just me.
Which one?
I don't know. Right.
You're welcome.
Are you running IBM? I don't think. No, not yet.
I hope so.
Yeah. Okay. But do you? And there's talk about, or for years there's been talk about abstraction layers and write once, run everywhere, and so on. Do you think that's a myth? Or, I mean, do you think that when you write something using an abstraction layer, you get something that works equally bad on all computers?
I mean, at this stage, if you compare where we are in classical computing in terms of layers of abstraction with quantum computing, we're very, very close to the metal, right? I mean, we're hand coding circuits with logical gates. That we haven't been at that stage since the 70s or something, or earlier in classical computing. So I think at this stage, abstraction, so Bracket offers one API interface to all the devices that are on the service. So there is a degree of abstraction there. However, writing a circuit to run on QuEra, or actually an analog Hamiltonian simulation now, but when you have a gate-based device, running a circuit for QuEra versus running a circuit on IQ versus IQM or Rigetti, they all have different topologies, they have different connectivity, they have different T1, T2 times. So of course you have to optimize for that specific piece of hardware at this time. So, abstraction can only do so much when we're so close to the metal at this point.
And Ikko, I'm curious. You guys introduced CUDA-Q.
Yeah.
Does CUDA-Q address this, or is it just a sort of marketing extension? Since CUDA is so popular, you put in a Q and say, "Oh, this is."
So CUDA-Q supports many hardware vendors. So you can use, for example, QuEra's hardware or AWS Bracket. In this Q2B IonQ, Quantinuum, OQC, many hardwares are supported. So in this sense, the CUDA-Q unifies high-level programming language, but this is just a high-level user interface. So in low-level or intermediate representations depends on the hardware providers. So we are QuEra member of QuEra Alliance, Quantum Intermediate Representation, and IBM is developing OpenQASM 2 and 3. So there are many types of intermediate representations. So I'm not sure we need to standardize these intermediate representations, but this is maybe a problem. I'm not sure.
And I asked Sebastian about multiple computers, but actually, Hanhee, when you go through various generations of IBM computers, the connectivity changes, the number of qubits, the capabilities. So how do users cope with moving to newer generations of the computer?
Yeah, I guess so. That requires some adoption time because I think it goes to more like a transpilation, right? If the connectivity is changing, then your transpilation will change. But I guess so, more like a learning curve. But it's still probably easier because the same types of quantum computer with a similar capabilities, similar performance, so much easier to use multiple quantum computers. But I think what you just said, like using QuEra machine and then IBM machine in the same with the HPC in the same programming environment, there can be a lot of beneficial. It could be a benefit, right, from some certain algorithms. But those will be probably more challenging in some level. Yep.
Let's talk a little bit about applications. And when people talk about quantum computing, they say optimization, simulation, and machine learning. But let's be real for a second. What do you see as the most popular type of application that your Amazon or IBM or NVIDIA are running today on hybrid environments?
At scale, as I said, AstraZeneca is the most notable recent example, and I think it's no accident that it's a pharma company, because I think that in terms of prospects for near-term economic impact, that solutions, when QPUs continue to mature, the first industries that are going to benefit, I think, are going to be manufacturing and pharma, because chemical simulations or quantum chemistry, material simulations, those are going to be the first things that can be effectively addressed through these hybrid HPC and quantum solutions, I think.
Me go first. Right now, IBM is working with ReCAN and then we show this first quantum and HPC, one of the first quantum and HPC algorithms, which is the sample-based diagonalization, where quantum samples the wave function with a lot of noise. And then we move that to HPC and then diagonalize to reconstruct the Hamiltonian to compute the energy in the higher accuracy. And then the newer version that we haven't really, we submitted to, I don't know whether I can say that. We submitted to some awards for the Computation Invitation Awards, but we actually have a new version of that where the HPC now is optimizing the quantum circuits to sample the wave function. So there's a more like a loop going on between back and forth to improve the accuracy. So chemistry is definitely the area we are looking at, or materials. And hoping that through this IBM Quantum plus MIABI, which is mostly GPU system, actually is NVIDIA system, we are hoping to explore also quantum and AI in some level. Yeah.
And Ikko?
We are we are doing quantum for AI, especially with database. Yeah, Sebastian explained already. So I want to show another example. For example, we are studying generative quantum eigensolver with University of Toronto and Central Children's Research Hospital. Generative quantum eigensolver is similar to VQE, but the difference is quantum circuit is not parameterized. So instead, generative model is parameterized, and this method can use transfer learning. So we believe this approach is more scalable. So AI for quantum is very useful.
It's good that you mentioned AI for quantum. NVIDIA published a technical blog of work that we did together with you guys, where you'd shown a very efficient AI decoder. So instead of measuring the syndromes for error correction and then doing a sort of classical calculation, looks like AI can perhaps help that. One of the things we see at QuEra, which we've had some success recently, is actually in quantum machine learning, where the hybridity is a lot of data preparation that's done classically and then running on quantum and then analyzing on the other side. We recently published a paper together with Merck and Amgen and Deloitte that showed that quantum machine learning outperformed classical machine learning on clinical trial data when the sample size was small. And you think, well, why would the sample size be small? Well, it could be a rare disease or it could be a very expensive treatment and you just don't have a lot of patients. And if quantum can get information faster or sooner, that's very interesting. I want to ask you a question, and after that maybe get one or two questions from the audience. So audience, please think about the questions you want to ask. Someone told me that physicists don't ask, how are you? They ask, what's new? They just care about the derivative. And since many of us sort of go to the same shows and see the same vendors, so I'd like to ask you, what's new? I mean, what's new right now in Tokyo that wasn't here in the HPC quantum world, say, 6 months or 12 months ago?
I mean, you've got a device that you're building here. That's probably the newest, since that's imminent that you'll be launching that device. I think it's really exciting what ICE is doing with the GQuad Center with NVIDIA, and the other devices that will be joining the QuEra device there. I think it's a tremendous resource for Japanese industry, and Japan has been, as a nation, I think, more dedicated, more invested in quantum from an industrial side and commercialization side than any other single country, in my experience. And I think that once GQuad gets up and running, the Q-Star Industry Association will be sort of part of the flywheel of identifying use cases of high value and developing them using the GQuad resource, and then deploying them into commercial applications as the hardware matures. So that, I think, is really exciting.
Hanhee?
So I have to talk about a new thing out of non-IBM, or can I talk about IBM?
Whatever you want.
Because we just made an announcement about the IBM Quantum Kawasaki system in University of Tokyo that will be integrated with MIABI, operated by the University of Tokyo and Tsukuba University. So again, the MIABI system is NVIDIA.
Yes, MIABI is.
Yeah, we are really looking forward to exploring the algorithms for quantum and AI. Yeah.
By the way, 2 weeks later, I will have a workshop using MIABI, quantum HPC hybrid workshop, MIABI-C and MIABI-G coupling. So this is heterogeneous computation. So Miyabi C is CPU nodes, and Miyabi G is GPU, our GPU class nodes. So it is a bit difficult to communicate with different types of nodes, but University of Tokyo group made weight IO to communicate the different architectures. So this technology will be used to communicate with HPC and quantum, I think.
I do have many more questions, but let's see if there's someone from the audience that wants to ask anything.
Hi, David Reichmuth here from TUM Venture Labs Quantum, startup incubator around quantum technology in Munich. So very much appreciate the mention of the LRZ. I have one question. So what I'm seeing more of is teams and students interested in startups going towards sort of load balancing and HPC integrations of quantum computers. And now you're all from fairly big companies, so I'm wondering if you see any space for those kinds of companies to come in, because they're finding it really difficult to get into the data centers and actually getting paying customers.
Well, QuEra, we're trying to make us look big, but in earnest, I was joking with my friends, you know, the big four on stage, NVIDIA, IBM, Amazon, and QuEra, right? We are 80 people today, so we're not that big. Yeah.
NVIDIA is actually
but
big.
yes, I think there's plenty of opportunity for startups because there's so many open problems.
That's
you know,
right.
from the programming layers to the scheduling to applications that take true advantage of that. But what do you guys think?
Well, I would go back to my point before about the fragmentation of tooling. I think that, actually an AWS ISV partner, Algorithmic, their technology is going to be used to some degree in the GQuat Center, as far as I understand. They just got acquired by Datadog, but they were addressing that kind of fragmentation and the need for modernization in data centers. And I think it's a good example of taking a problem and trying to just very narrowly focus in on a solution for the operators of the data center, of the HPC center.
Did you mean agnostic or algorithmic?
Oh, sorry, agnostic, yes, thank you. Yeah, covalent, exactly, yeah.
Anyone else want to answer that, or?
I mean, to be honest, I guess the solution, providing solutions using quantum and HPC, again, is a new infrastructure. And then using that solution, which is algorithms basically, as a product is actually a big business model. So a lot of times HPC is offered in a very cheaper price because HPC is a potentially developed, like for example in Japan, Fugaku, you can just apply it. And then if you're, I believe, I mean, I'm not sure how much you have to pay, but you know, it's not like maybe I don't know. Actually, maybe I should. But a lot of times the resources can be available, you know, especially for the startups without government support. So, but I think again, the solution development will be a kind of good direction for a startup in this case.
Yeah, if you open the result, Fugaku is very cheap, and there are many opportunities to use HPC and quantum. For example, NEDO Challenge is a contest of solving a social issue using quantum computers. So now they are, so you can apply your proposal to solve their issues. Then you can use resources like ABCIQ or JHPC, JHPC quantum resources for free. And there are another opportunity. JHPC quantum projects starts test user program. This is like a research project, but this is also free. So there are many opportunities.
Any additional questions from the audience? Please.
Thanks. I'm I'm Yoshi Shimada from SoftBank. Actually, I'm a pretty much heavy user for the JHPC quantum. The quantum sampling-based diagonalization, actually. But my question is how do you deal with the difference between the HPC culture to the not that against to the quantum culture, but also the cloud itself is quite different. System architecture is quite different, and also they always use Python code, or they do not use MPI code. So how do you deal with, or how do you integrate it, or just neglect it?
Very difficult. No, I mean it has to do with applying the strengths of each of those cultures or those resources to the parts of the overall problem that they're best suited for, right? I mean, you're not going to convince someone with an on-prem HPC cluster to forget about it and use something in the cloud, but there may be resources in the cloud that they don't have available in their HPC center. And then the challenge is, well, how can you efficiently leverage something novel in the cloud in an integrated way? So for example, Slurm, there's a plugin for AWS that uses parallel clusters. So that's an easy way to do a hybrid on-prem cloud kind of solution. And I expect the same sort of novelty and inventiveness is going to come through the introduction of quantum on-prem and quantum cloud as well.
Why do HPC centers exist? I mean, seriously, they exist because to solve problems for customers. Yeah. They don't exist to buy GPUs or quantum computers or so on. So what we are seeing is that forward-thinking HPC centers are saying, well, quantum is an opportunity, not the goal by itself, but an opportunity to help our customers solve problems that they couldn't solve before. And therefore, they're setting up quantum teams to help educate their users, to help say, you know what, this is really a classical HPC problem, or this is more of an exploratory one, and try to make it easier for users to get to the next step. Yeah. I want to ask a question, but in the meantime, if someone has a question from the audience, why don't you raise your hand so that the microphone could get there faster? But let me ask the question. When you think about cloud services, one of the value proposition of cloud is when you need more capacity than you have on-prem, then you could sort of spill over to the cloud. How far are we from that being applicable to quantum?
Make more than one device, Yuval.
Oh, we make many. You just need to get them on your cloud, right? I mean, just like earlier when you said when you make a digital device, we do have a digital device. We just needs to be on bracket, right?
It's coming.
Yeah.
No, I mean, I think, I said parallelization before. I think that is something that's going to happen. Actually, not to mention a competitor, but IonQ now has 2 Forte devices on bracket. And we're looking at a couple of different projects that may take advantage of those 2 identical devices or nearly identical devices to run 2 parallel quantum workloads as a sort of proof of concept of exactly what you're talking about.
And Hanhee, do you see that? Do you have on-prem customers that kind of spill over to an IBM cloud?
I'm not sure whether it's technically possible at this point, but we actually do think about multiple QPUs because when we are running these SQD algorithms, that it'll be great to run or sample multiple wave functions to putting into HPC because HPC can compute more, they can handle more data. So why don't we just have a more quantum data putting onto HPC, right? So this multi-QPU will be probably the next direction that we have to explore.
Is that something that you guys are thinking about, Ikko?
Me? No. IBM? Yes. Yeah, I think so. Absolutely. Yep. Absolutely.
Did the microphone get to someone with a question or? Nope. Okay. So next year in Tokyo, what do you hope to see that you haven't seen this year?
Let's have Ikko first.
Let's have Ikko first.
Of course, ABCIQ starts. We can use QuEra's quantum computer. We can use our GPU's supercomputer. Yeah, I want to see the use case and research papers from users.
And then in Japan, anyone would be interested in multi-QPU IBM quantum computing system? Actually, by the way, since IBM Kawasaki is connected to Miyabi, and then Miyabi will be connected to Fugaku. Fugaku will be connected to IBM Kobe, which is coming in June. So actually, we may be able to demonstrate some multi-QPU with Fugaku or multi-QPU with Miyabi next year. Yeah, we'll see.
You can have the QPU Olympics, right? And Sebastian?
Ikko mentioned ABCIQ and the GQuad Center being up and running with QuEra and potentially other devices. I mentioned QStar before. I think that globally the challenge is soliciting problem statements from industry that are relevant and looking for the parts of the end-to-end solution that maybe HPC or classical now, but could yield to a quantum information approach, and then the development of those use cases. I think that's the most interesting area right now that I see. So that's where I hope in a year we've got more examples like AstraZeneca, but that are coming from QStar, from Toshiba, from Fujitsu, et cetera, and running on the GQuad Center.
And we think there's no use case without you. So we're looking for you to come up with some use cases and some really cool stuff. So thank you very much, Ikko, Hanhee, and Sebastian. Thank you for being here.
Thank you for inviting us.
Yeah, thank you.